Okay, in today's lesson, we're going to be looking back at what we've done so far on series and parallel circuits and the rules that we learn for them. So what we want to do is to be able to apply these rules to find the potential difference and current and resistance in some cases in series and parallel circuits. And we want to be able to state the rules, want to be able to apply those rules to find the current and potential difference in different places. And using this understanding, at the end of the lesson, you're going to answer some exam-style questions. Okay, so I'm going to get started straight away with series circuits, and then you're going to have a little bit of work to do for each bit, in which part you're going to have to pause the video and do the questions. So this is a series circuit, as you should know by now. So we can see it's a series circuit because there's only one loop that we can have going around the circuit. So we just got our electrons flowing all around, our charge flowing all around the circuit. It has to go through both of the bulbs. Okay, now in here we've got two identical bulbs and one cell or battery. So we're going to have a think about what the rules are for our series circuit and what that's going to allow us to work out from this. So first off, let's have a look at the current in the series circuit. So we should remember that one of our rules for series circuits is that the current is the same in all places. So if, for example, we have a look at the current over this side is 0.45, we can predict that if I put an ammeter in a different place, so let's say, for example, I put an ammeter here as well, and the question might ask you, what is the current at this part here? So you want to work out what that is. So based on this information, that the current is the same in all places, I should be able to work out that because it's 0.45 here, then the current must also be 0.45 amps here as well. Okay, now we're going to look at potential difference in a series circuit. So first off, we need to remember our rule for potential difference in series. Our rule being that potential difference is split between the components. So what that means is that whatever the potential difference of the total circuit, or for example, the total circuit is always going to be like your cell or your battery, that's going to be divided between the components that we've got, in this case, the bulbs. So in this first example, if we look, we've got a total potential difference for this first bit of 9 volts, because the battery itself, the cell, has 9 volts of potential difference. So each coulomb of charge is getting 9 joules of energy, so it's 9 volts. So if we look at these two bulbs, they are identical in this one. And in the question it might tell you these two are identical. So how would that 9 volts be split up? Well, because they're identical, it would just be split in half. So bulb number 1 is going to get a potential difference of 4.5 volts. And bulb number 2 is also going to have a potential difference of 4.5 volts. Okay, so that's nice and simple when the bulbs are equal, and that's because the bulbs are identical, so it splits equally. Okay, but if we have a look at the second circuit, we see again we've got a 9 volt supply, so this one a different colour. So again we've got a 9 volt supply, okay, to start us off, 9 volts. But this time, if you look at the bulbs carefully, you'll see that one is brighter than the other. So if we just call these bulbs number 1 and 2, we can see that bulb number 2 is brighter than bulb number 1. And if we have a look at the potential difference of these, so let's have a look at bulb number 1 first. Bulb number 1 has a potential difference of 3 volts. Okay, so bulb number 1 is 3 volts. So if I was given this information, I should now be able to work out what the potential difference of bulb number 2 is. Because I know that the total is 9, bulb number 1 is 3 volts, so bulb number 2 must be what's left, which is 6 volts. Okay, so bulb number 2 is 6 volts. So because they're not equal, because they're different bulbs, we don't just divide it by 2, it gets split up a different way. Okay, so it is still split between the components, it's just not split equally this time. So now we've gone through the rules for series circuits, I'd like you to pause the video in a second and have a go at some of these questions. So I'll just talk you through them a second first. So first off, I'd like you to state the rules for current and potential difference in series circuits. So if you're stuck on those, if you've forgotten them already, I'd suggest you go back, watch the first bit of the video again, and it goes through the rules there. I have just gone through them, so you can go back, and that's the beauty of things being on the video, you can go back and watch them again as many times as you need to, and make sure you write them down. Then I want you to work your way through these 3 questions at the bottom, so question 3, 4 and 5. So using those rules, and we're now trying to apply it to different situations. So in these different examples, you've given some information, and remembering what the rules are, I want you to try and work out what the current and potential difference is going to be in each of these places. Okay, so I'll let you have a go at that now. So pause the video now, and then when you start again, we'll move on to parallel circuits. Okay, now we're going to move on to have a look at parallel circuits. So we've got 2 parallel circuits here, and you might notice already a bit of a difference between them in terms of the way that the current or the charge is moving around the circuit. So we're going to start off by looking at the current in parallel. So you should remember the rule for this is that in parallel circuits, current is split between the branches. So whatever the current is at the top, where the battery is, or whatever the current is through the battery won't always be at the top, which is a point we kind of need to remember on this. It gets split up between the different branches. Okay, so in this example we've got here, if I get my ammeter out, we've got the first one where we've got 2 identical bulbs. So if I look at the top, we've got a current of 1.8 amps. So if I take that and I write that down at the top, my current is 1.8 amps. Now because these are identical, if you look here at this little bit where the current is splitting up, okay, you can see that every time one goes, it's going one this way, one that way, one this way, one that way. It splits equally because the bulbs are identical. So that 1.8 amps will split into 0.9 amps in the bulb number 1. So this is bulb 1, is going to be 0.9 amps through that first branch. And for bulb number 2 at the bottom, it's also going to be 0.9 amps. So that's number 2, 0.9 amps. So that's because the bulbs are identical, it's going to split equally. But what if the bulbs aren't identical? Okay, so let's have a look at this one here. So first off, we'll find the total current again. So the total current this time is going to be 2.4 amps. Okay, so total current at the top is 2.4 amps. Now if you look though, this is not splitting equally. We can see that the current is moving much faster through the bottom. There's much more current, much more charge per second flowing through the bottom bulb. So if we have bulb 1, bulb 2, there's much more current flowing through bulb 2 than there is through bulb 1. And this tells us something about the resistance, okay? So first off, if there's less current going through, then bulb 1 must have a higher resistance. Okay, this is before we even know numbers. Okay, so because it's got less current, it's got more resistance, and the bottom one is going to have a low resistance. Again, because we know that because there's more current flowing through. And that's just by looking at this. Well, let's get some numbers together now. So first off, if we have a look at this one, we can see that through bulb 1 there is a current of 0.6 amps. So going through here, there is 0.6 amps, and there was 2.4 flowing around the top. So we should now be able to find out what was going through bulb 2. To do that, I would do 2.4, take away 0.6, and that will give us a total of, and if we have a look, we should be able to find that out, it's going to be 1.8 amps. Okay, so 2.4 minus 0.6 is 1.8 amps, and we see that there is 1.8 amps flowing through the bottom. So this tells us that there is more current flowing through the bottom, and therefore there is got a lower resistance through the bottom bulb for bulb number 2 than through bulb number 1. So we can use this to calculate the current at different points, and it also tells us a little bit of something about the resistance. Okay, now we're going to look at potential difference in parallel circuits. So we should remember again, the rule for this is that potential difference in parallel circuits is the same across each branch. So what this means is, it doesn't matter what the bulbs are in each branch and how big their resistance is or what the components are, it's always going to be the same potential difference in each place. So let's start with this first circuit. So if we have a look at the potential difference at the top, okay, on the first battery, we find that it has got a potential difference of 9 volts. And we know that these bulbs are identical. And if we have a look at moving this down, so I'll move that there so you can see it a bit better. If I move this down, we find that across bulb number 1, that is also 9 volts. And we should see that is 9 volts across the bottom as well. So if I do move that down, we can see it's 9 volts. So in this first circuit, the potential difference is exactly the same on each bulb. Now, if we compare it to the second circuit, now this is a different battery, I think. So, oh no, it's not, it's the same battery. So this is 9 volts. And even though these bulbs are different, they also have a potential difference of 9 volts each. And this bottom one will be 9 as well. I'll just prove that to you. And that is because the potential difference is exactly the same across each branch in a parallel circuit. And this is to do with the fact that the current has to be pushed through bulb number 1 or bulb number 2, not both. So it doesn't need to share the energy out between them. It can push it through this one or this one with the same amount of energy. Just push the charge around the circuit through either of them with the same energy, with the full amount of energy available to it. Okay, so again, similar to what we did with series circuits, we've gone through the rules and given you some examples of how this would work. So now I'd like you to have a go at answering these questions for me. So question 1 and 2, similar to what we saw last time, I want you to state the rules for current in parallel circuits and potential difference in parallel circuits. And just like I said earlier, go back through the video if you're not sure on those and watch it again to just make sure you double check that you understand totally what they are. Then questions 3, 4 and 5. So questions 3 and 4, you just got one question to answer, looking at these two circuits and first off working potential difference for the first one and the current for the second one. And for question 5, there's two parts to this. Part A is calculating the current at A1, and part B, I want you to explain which one would have the highest resistance, making sure you explain what your answer is and why you came to that answer. Once you've done this, You will have also been sent through some exam questions to have a go at. And again, if you just answer those on paper, that is absolutely fine. But you need to be getting on with those and asking if you need any help with them. And that should be taking you the rest of the lesson. So once you finish with these, make sure you have a go at the exam questions as well, please. And that'll be it. Once you've done that, we can leave it for today.